a pleasure to be here. Thank you very much for inviting. It's like so nice to be among the experts in this field and like really learning like so many things. So I'm going to talk about this tail probabilities of stochastic six-vertex model. It's joint work with one of my collaborators, Guilherme Silva from Sao Paulo University. And this is mainly a story, let me just tell you up front. It's a story of a failure, which I was kind of trying to solve a problem for 5 years. And like there's some progress we just recently made. It's not the full problem is solved, but I'll try to tell you like what are the challenges, why we're interested in this problem, and what are the big things you can achieve if you can solve this problem. Let me try to. Okay, thank you. Okay, so this is the plan. So I'm going to talk about a little bit about this stochastic six-vertex model. Although I know like you have been like informed about this model so many times, I'll still take this chance to introduce you one more time. So then I'll also talk about the exact problem that I'm going to talk about. So this problem has connections with this models you probably heard about, this KPZ equation. So I'll try to make this connection, that why and how this problem would be connected to this KPZ equation. And then we'll state the main results and the like some proof ideas. Like I'll not be able to tell like too many things, but some key ideas. Okay, so the way I would try to introduce this stochastic six-vertex model is slightly different than like the other speakers introduced, and it would be like mostly following this notion developed by Borodin, and Corin in their seminal paper in 2013. I would think, so the stochastic six-vertex model, the one we discussed now, were introduced by Guo and Spohn in 1992. And the way to think about it is that it's a probability measures on the set of directed paths, which is like infinitely extended. We can talk about the probability measures on a set of paths on a restricted domain, but then the challenge is that how do you extend it for the set of paths which are like infinite. So that's sort of like how we define, and I'm going to tell you how we do it in the next slide. And the initial data would be dictated by how the paths would be entering to this quadrant from the x-axis and y-axis. So we would be mostly focused in the case where it's a step initial data. That means like all the paths are entering from the x, through the y-axis. Okay, so the way to extend this probability measures, like for the set of all infinitely extended paths, is to sort of first define it for a finite domain, and then introduce a Markovian evolution, which would sort of eventually as a limit with the measure on set of all infinite paths. So we first have a set of path configuration on a triangle like this. And depending on how this path landed on this diagonals, we'll try to do a Markovian evolution of this path to extend it to the next diagonal. So for instance, if a path which is sort of coming to a node on this diagonal, like from the vertical direction, so we'll toss a coin with probability B2, and if it turns out to be head, then we'll go on the horizontal direction for the next node, and if it turns out to be tail, then we'll take a will go to the vertical direction. And for similarly, if a path is like hitting a node in a vertical direction, like here, so we'll toss a coin with a probability B1, and if it's like head, then we'll go straight up, and if it's tail, then we go to the right, towards the right direction. So this is like a two-parameter family of like describing the weight, this weights to this configuration. But there is also this another reparametrization of this parameters, and this is more sort of like the well-known, I think, like the most of the other cases where it is introduced. You have seen this choices of parameters in terms of Q and U. So we will interchangeably use this like parameters, but I will tell you like how these two set of like choices are related with each other. Okay, so once these probability measures are defined for this all paths, we would be sort of dealing with one function, and we try to study the like properties of this function, and that is this height function that like also have come across so many times. So the way the definition goes here is that, so for any given node, we'll try to see that like how many paths we have to sort of cross from the left to come towards that node, and that count would be the height function at that node. Okay, so the first thing which would come in our way and which would motivate our results towards finding something interesting is this Tracy-Widom limit of this height function. So if we start our stochastic six-vertex model, this Markovian evolution from the steep initial data, and if you run it for a long time, what do we see? So we'll see that like on the like upward direction, like on the upward side of this diagonal, most of the sides are filled with they're compactly filled with this edges, and whereas on towards the x-axis there are almost like no sort of like edge hitting those nodes, and in between this like fully filled up nodes and like the unfilled nodes, there is this funnel type region which has a width which depends on the ratio between these two parameters B1 and B2. And there are like this sort of lines which are sort of like going to like along a particular direction in that like funnel type region, and if we follow any of this line, there's some like interesting behavior fluctuation we would notice, and that is what like sort of came out in this work of Borodin, Corbin, and Gore in 2013. So what they showed is that if we follow any of this line in this funnel type region and look at the height function along those set of points and properly center and scale them, like according to this scaling and centering proposed by this KPZ scaling, then there is a limit, and that limit will be this Tracy-Widom GUE distribution, which sort of appeared in this before in this limit of the largest eigenvalue for this random matrix models. So this was like a long time behavior of this height function. But what we would be interested in is more like a quantitative understanding of this height function for any given finite n. And I'll try to tell you like why that would be something interesting. So one of the problems like people try to understand is that if you look at this funnel type region, and if you have a slight different kind of like inhomogeneities in this like like the arrows, like for instance, if you introduce some color, then how this colored paths would move along this funnel type region. Does it like follow one particular direction, or is it like a sort of like assemble among all directions? And for understanding the more like this, the inner geometry inside what's going on inside this funnel type region, you need this more fine-grained understanding of what's going on with the height function for any given finite n. And so this limiting results would tell you something, but you need a little more, and that's where we were going. So what would help us towards achieving this goal is one identity, and I will tell you that identity, but then it's came through a connection with an orthogonal polynomial ensemble. And I'll introduce that first, and then we'll tell you this about this identity. So it's related to it turns out the stochastic six-vertex model height function is related to Meixner ensemble, and it's like set of probability measures on like particles on positive half of this the positive half of the real lattice, and the probability measures is described by the square of van der Mond times the Meixner product of the Meixner weights, where the Meixner weights has this following structure. Now there is this interesting identity which came up in the work of Alexei and also like a separate work of Alexei with Olshanski, that this if you take this height function for the stochastic six-vertex model and take this interesting type of expectation, which is like this product of like 1 over 1 plus q moments of this q power of the height function shifted by this number I, then this expectation is equals to some multiplicative functional of this Meixner ensemble. And this description is true for any finite m and n. Now, this does seem like just like an innocent, just like identity, and and it's cool to have this identity for different cases. In fact, it's like also it's appeared similar identities are like been proven by Alexei and others, and for many other models. I'll try to tell you a little bit of those later. But what is nice about this identity, I'm going to tell you in the next slide, and that would be sort of how we set the goal for this talk. So what we want to do is that do this asymptotic analysis, like more like the for any given finite n, how this like the multiplicative functional of Meixner ensemble behaves. And through that, we want to achieve this understanding of the tail probabilities of the stochastic six-vertex model. So especially the one of the tail which is like turns out to be very hard to find is this upper tail probability, and that could be like found out from using this multiplicative functional of this Meixner ensemble. And the way to do it is like kind of like written down in this lemma. It's not very hard to prove. It's some like algebra. It turns out that like up to sacrifice of some epsilon factor, if you look at the scaled version of the height function that I introduced, which converges to this Tracy-Widom distribution, then this upper tail probability of this like scaled height function is upper and lower bounded by this multiplicative functional of the height function, which is related to this multiplicative functional of the Meixner ensemble. So in fact, if you have a very good estimate of this Meixner ensemble functional, then you would have this good estimate for this height function. Yes?
Does the upper tail here correspond to upper tail Tracy-Widom or lower tail?
Lower tail Tracy-Widom, yeah. So this is the kind of the hardest thing to achieve. Just to tell you like about the other,
is it clear that when epsilon is small, the right-hand side is small?
So epsilon, I'm just like, it's a kind of a dummy variable, so you can set it to be like any small value. So it doesn't affect the upper bound that much. The lower bound would be somewhat effective. So if you try to make the epsilon to be smaller, there's something bad would happen. Yes, so here you cannot make it too small, so that would be like 0. So that would be exponential 0. exponential of 0, which is 1, so we cannot make it too small. So lower bound would get affected, but upper bound is not too much affected. The only problem is that if I take this epsilon to be 0, I have to move this h, which is sitting in the zeta. Like I have to move it by some amount, but it should be upper bound. It should be okay. And so just to give like a comment about the other tail could also be written down in terms of this multiplicative functional. It's like a little more easier. And there are other ways to find like the estimates for the other tail. So we'll sort of mostly focus on this upper tail probability, which is hard to obtain. Now this is the goal, but what I would do is that I will take a departure from the stochastic six-vertex model for a few minutes. I'll talk about the more general case, which is the random matrix model. But I promised that I would come back to the stochastic six-vertex model very soon. So the thing is that like this understanding this multiplicative functional of the Meixner ensemble, you can ask that why like so when we started studying it, like there are like we faced a lot of difficulties, and then asked like, okay, so can we just do it for a more simpler case? And maybe if you understand it, if we achieve something, we can redo it for the Meixner case. And one of the simple case one can try to study is that just the usual random matrix model, unitarily invariant random matrix model with this distribution on the eigenvalues with certain potential. And you can ask like, what if we take the multiplicative functional of this random matrix model? How does it behave? Does it give any information? And if you can achieve that, can we use the tools from there to like study this Meixner ensemble? So that's exactly how we proceeded. That's why it took quite a long time to finish this project. So we had this random matrix model, and the multiplicative functional that we consider is like is exactly kind of the similar form. It's only the differences that we choose a scale for this functional like that we have used for the random matrix model, so that like the scaling operates in a way that it sort of like magnifies this multiplicative functional at the edge of this random matrix model. So you get to see this Tracy-Widom behavior, not only just the Tracy-Widom, but sort of accumulation of the eigenvalue at the edge, and that would have some effect. One thing to notice here that like I put a general function, like Q is like at this point I'm like keeping it as general as possible, but you can just ask the same question for just a linear function. Okay, so this was what we found in a work 2 years ago, and that sort of like was the kind of driving force for us to complete this project for the Meixner ensemble. So what we found that like for this general matrix random matrix model, if we choose this potential to be even degree potential with equilibrium measure being like 1 cut, then this the logarithm of this multiplicative functional that we looked at is given by something very interesting, is described by integral differential Painlevé equation. And this is what it looks like. So we were not only able to find the limit, but also like how fast this multiplicative functional converges to that limit. So that's sort of expressed in here. So this exponent that you see, it's like in between 0 to 2/3, but like the optimal estimate, optimal value should be actually 2/3. What is interesting about this is that like this integral differential Painlevé 2 is like very close to this Painlevé 2, just like there's, if you forget about this integral inside this integral differential Painlevé 2 is exactly Painlevé 2. And that's what actually described the Tracy-Widom GUE distribution, this Painlevé 2, exactly like if you replace it, this phi by just solution of Painlevé 2, then it describes the Tracy-Widom-Dewey distribution. So this is like this indicates like a positive deformation of this Tracy-Widom-Dewey distribution in some sense. But we found this result, but it's not actually like unexpected, and I'll try to tell you why. And that's how we try to connect it with the KPZ equation. So the scaling that I told you, like we chose it in a very special way so that when we send this n, the number of particles for the random matrix model, to infinity, it converges to this, expectation of multiplicative functional of Airy point process. So basically this random matrix model at the edge converging to this Airy point process, and that's where that's what is showing up in the limit. So the scaling is chosen in that particular way. So the integral differential Painlevé 2, which we found as an alternative limit, should be equals to this expectation that we wrote down here. Now, if you believe in this, this was kind of also came out in other works. So Borodin and Olshanski has a paper where in 2016 where they showed that this multiplicative functional of the Airy point process is related to double exponential moments of KPZ equation, where this so the right-hand side of this identity is this double exponential moment, and it's where this z is the solution of the stochastic heat equation. So logarithm of the z is the solution of the KPZ equation. So so I try to so this is where this KPZ equation appears. So just to tell you like how actually KPZ equation would look like. So it's unlike this stochastic heat equation, which is the has just like the second derivative of like with respect to spatial variable times multiplicative white noise. The KPZ equation has a like complicated like square of the slope term, and like as many of us know, like it leads to this like the white class. It kind of governed a large class of physical model, and the scaling limit of the KPZ equation coincides with the scaling limit of any random growth models. So it's a like important object to study. Now, why I'm telling all these things, like how this is connected to the stochastic six-vertex model, and this is where we were kind of trying to go in the next slide. So what happened for the stochastic six-vertex model, not only on the KPZ scaling, it converges to the Tracy-Widom-Dewey distribution, but also it under certain limit, it also converges to the KPZ equation itself. Now, how did it happen? So if you look at, this is the picture that we have seen like in first few slides. So this is the funnel region which would be created. Now suppose that we take this asymmetry parameter, which is B2 over B1, we make it close to 1. So this funnel would sort of try to be collapsing towards the diagonal line. Now, if we still take a line which is inside this collapsing funnel region and go very far along that line and try to find out, try to zoom in the set of paths that we see at a very far away points, the paths would look somewhat like this polymer paths. And that's kind of indicative of like fact that it might converge to under some scaling limit, it would converge to this KPZ equation. And that was indeed the case. So I had a paper which like almost like 6 years ago, which showed that like if you take this asymmetry to be converging to 0 in a certain way, and if you take this like diffusive scaling of the space and time, then this height function of the stochastic six-vertex model started from the step initial data under certain centering and the scaling converged to this narrow edge solution of the KPZ equation, which is this logarithm of the solution of the stochastic heat equation. And this result uses to prove this result, we have heavily used this Markov self-duality of the stochastic six-vertex model. Now, how this result is connected to the story that I was telling you, this integral differential Painlevé. So what happens is that the consequence of this result, the convergence of the stochastic six-vertex model towards this Capes equation, is that like if we take our this zeta in the multiplicative functional in a right way, and take this asymmetry, of course, we are sending it to 1, then this like limit of this multiplicative functional actually converge to this double exponential moments of the Capes equation, which is equals to this integral differential Painlevé 2. So what this shows is that in the limit of this multiplicative functional of the Capes of the stochastic six-vertex model, which is multiplicative functional of the Meixner, we recover integral differential Painlevé 2. But the question that we actually interested in is that like we want to fix this asymmetry parameter q, like you don't want to vary it. And for a fixed q, can we have a description? So that's the sort of question, the main question that we want to ask. So I just want to sort of prepare us towards our main result. So we're going to see two different type of special function in the description of this tail probability. The first one is Painlevé 34. So I think I know this page looks a bit scary, but just bear with me. I'll try to explain a little bit later. It's a PDE and there is this Bessel function which has a certain expression, and then we would consider an expression constructed out of Bessel function, like in this following way. Also, this d and d tilde would be the sort of driving factor for the description. Now, here is the main result. So it turns out that, like, if you look at this multiplicative functional of the height function, description of it, like, or at least the leading time behavior of the multiplicative functional, it changes as we vary n. And in particular, it depends on, like, in other words, it depends on at what level we want to understand this tail probability. So in the tail probability, remember there is this h. So we want to understand the tail probability of the height function being greater than this h, and it depends on how large this h is. So, so for instance, that if h is like multiplied with n to the power 1/3, lying in this interval n to the power 1/3 to n to the power 1/2. Sorry, minus s naught times n to the power 1/3 to n to the power 1/2. Then there is a asymptotics. There is a uniform asymptotics given in terms of d, which has this Painlevé 34 in it. And if we go beyond n to the power 1/3 on the negative side of for h or for s, then the switches, the leading term actually would be described by the Bessel function. And but we had to stop at n to the power 1/2. And you may question that, why do we have to stop, and what do we expect beyond, even beyond that? Like you can, the ideal thing would be to ask, like, what would happen starting from minus n to n to the power 1/2. We didn't have an answer for that, but there is a guess what could happen. And so this is how the multiplicative functional would behave. Now let me try to tell you that what implication it would bring for the tail probability of this height function. So first of all, like the Painlevé Painlevé 34 is not very far from Painlevé 2. There is some like very concrete relation between these two. And the tail probability in particular here, so if our level at which we want to understand the tail probability is in between some fixed value minus h to, sorry, this should be plus, there should be minus h in between h naught and n to the power 1/6 minus epsilon. If h lies in between these two limits, then the tail probability would exactly behave like the Tracy-Widom GUE lower tail probability. This is how the exponent would look like for the Tracy-Widom. And if it goes, on the other hand, like we have also a description for this upper tail, as we were saying, like the an upper tail, or rather lower tail for the stochastic six-vertex model, and the lower tail would behave like upper tail for the Tracy-Widom GUE, which is like has the behavior h to the power 3/2. Now the speculation is that if you go towards the large deviation regime, where h would actually be, would be of the order n to the power 2/3, then the tail probability should be given in terms of integral differential Painlevé 5, but that's still not clear how it could be like provable. Okay, so how much time do I have? Oh, there's. Oh, yeah, okay. So I think I have a lot of time. So, so I'll just tell you like what is the main like building blocks for this proofs, and I'll stop. Like I won't go too much details about. So what exactly drives this proof? What is the key idea behind? Like, and then like what? Oh, and then like this key idea was the one like which we had to struggle quite along to get along with. And but the previous approach that we are taking like turns out to be too much like complicated to complete. But this there's one simple identity kind of changed the whole landscape. So it turns out that like this so we want to understand, or like we want to understand the asymptotics of this multiplicative functional of the Meixner ensemble. And it would have some like the determinant formula, and you can like try to understand the asymptotics for the kernel of the determinant, but that's the bad move to do in this case. Like if it leads to complication which could not be dealt with like in a finite time. So rather what we did is that we found an intrinsic identity which relates the logarithm of this multiplicative functional in terms of integral of a Christoffel-Darboux kernel. This identity, like it's a very simple to prove. It's like would probably take a one page, but it just like if I don't write it down in this way, it's kind of hard to believe that. Like so, in general, like the L would be written in terms of some like determinant of this kernel K, but then why this logarithm of L would be written down as integral of a kernel K, that's a bit not very straightforward. So, and this kernel K is just like the kernel which appear in this appear through this like the orthogonal polynomials for the specific weight that we choose. So in this case, like we started with the Meixner, but since we have to sort of deal with this multiplicative functional of the Meixner, we have to deform this Meixner weight. So the W was the Meixner weight, but we had to deform it by multiplying the Meixner with a factor 1 plus q, zeta times q. And the P is this orthogonal polynomial coming from this this deformed weight. Yeah.
So what you're saying is that there is no direct link to the trace of anything.
No, I mean, so this ln you can bound it like by trace of k. There is this Widom trick people use, but that would be just upper bound. Like if you are interested in both upper and lower bound, then you have to get some like exact identity, and this would sort of like help us to get this exact asymptotics through that way. Okay, so then the rest of the thing is like we had to rely on this age-old technique of Riemann-Hilbert problem. So we looked at this deformed, the kernel coming from this deformed Meixner weight, and it could be expressed as a function of some matrix valued function, as a some functional of matrix valued function, and this matrix valued function x satisfy this Riemann-Hilbert problem. And the challenge is mainly actual relies on the for different choices of S, the residue structure of this matrix valued function is changing. And so the behavior of or at least the leading order behavior of this matrix valued function also change as we kind of scale the S higher up. And to kind of to understand this, what would be the leading contribution, we have to test the what function could fit the residue structure of this matrix valued function locally around this point A. So for instance, in this two regime that I showed you, in one regime it was solved by this Painlevé XXXIV, and in other regime it was solved by this Bessel kernel. And the speculation is if you go to this more large deviation regime, it should be solved by this integral differential Painlevé V. Okay, so I'll just probably finish it early. So so we looked at the tail probabilities of this stochastic six-vertex model in the KPZ regime. KPZ regime is like when we're scaling this the fluctuation of the height function at the n to the power 1/3 scale. And we extend it to the critical regime. And the critical regime, I should say that it's just close up, it just stops at this right before the central limit theorem type of scaling, this n to the power 1/2 scaling. So in this negative KPZ regime, which is basically governing this tail probabilities, this upper tail probabilities at the KPZ regime, is governed by this Painlevé XXXIV, and this negative critical regime, which is going a bit higher up, is governed by this Bessel differential function. And but one nice thing about this is that the identity that I showed you, it's now it's provable for any multiplicative functional of any discrete or continuous orthogonal polynomial ensemble. And so this trick of finding this asymptotics of these functionals would work in general for other cases. So the open direction is the immediate open problem is to extend this analysis in the large deviation regime. To get this, it's possible with the whatever expression we have to get some estimate, but to have exact asymptotics, it's a little more sensitive. So what turns out, as I mentioned before, that other models, which sort of belongs to this KPZ universality class, also satisfy similar identities. So for instance, ASIP does have an identity which is related to this discrete Laguerre ensemble, whereas stochastic higher spin vertex model is has this relation with this McDonald measures. So for all these cases, now the tools that we have, one can extend this analysis in those setup. Now another interesting thing which came up through this sort of different way of viewing this problem is that this multiplicative functional, if we proceed in more conventional way, historically how people used to think is that to define a operator-valued Riemann-Hilbert problem for that. But with this, viewing this multiplicative functional or logarithm of the multiplicative functional as integral of this kernel, you can now like do this analysis for like this kernel and bring in some integrability for this operator-valued Riemann-Hilbert problem, which was not clear before, and doing it in a more systematic way actually would solve this big problem of like producing this integrability of this operator-valued Riemann-Hilbert problem. So this is sort of like where probably the rest of our follow-up collaboration would be concentrating. Okay, so I'll stop here, and I'll be happy to have like, questions.